This is part one of the lectures on relativistic dynamics. So far, with respect to the theory of special relativity, what I've given you is a brief run-through of basic relativistic kinematics. It's as if we went back to chapters 2 and 3 with the mathematical description of motion, and then therefore, if we describe motion in a relativistic manner, we then end up with the effects that we've seen: time dilation, length contraction, and so on. So now what I'm going to do is give you a taste of relativistic dynamics. For example, what happens if you take forces into account, what happens with mass, energy, momentum, and so on. So then therefore we begin a basic look at relativistic dynamics. Okay, here's how we're going to approach this. What we're going to do is we're going to examine a very specific type of collision, a one-dimensional, perfectly inelastic collision. If you recall from momentum, this then means that the objects stick together after the collision. We're going to set up the simplest possible case. The simplest possible case is going to involve two objects of equal mass. And then with respect to a stationary observer, initially those two objects are moving in opposite directions with the same speed. And then with respect to that stationary observer, after the objects collide and stick together, the objects then therefore will end up at rest. And then what we'll do is we'll examine the exact same situation, but in the second case from a moving observer. And that moving observer, that moving reference frame, is going to be initially moving along with one of the objects prior to the collision. We'll take into account the Lorentz transformation as we do. So let me go ahead and set up this situation. Okay, so relativistic dynamics. We're going to consider a one-dimensional, perfectly inelastic collision between two objects of equal mass. Okay, now according to the stationary observer, the following happens. So now according to O. Okay, so first of all, here's this object here of mass m, initially moving to the right-hand side with velocity v. Okay, right over here is the second object of mass m. Its speed to the left-hand side is also going to be v, but we'll have to take into account a negative sign when we consider this to be a velocity vector. Okay, now let's go ahead and total up the momentum of the system prior to the collision. We're just going to refer to this as P initial. Okay, now recall that momentum is mass times velocity. So then therefore we have the initial momentum of the first object here, just simply mv. And then the initial momentum here of the second object is going to be m, but then multiplied by negative v, because of course that velocity vector points to the left-hand side. Add this up and you end up at 0. Okay, and then the two objects stick together after the collision. Remember, it's a perfectly inelastic collision. So here are the objects like so, m and m. They have a final velocity here, we'll call it v final, that's equal to 0. So then therefore the final momentum of the system is going to look like this. 2m times v final, and that's equal to 0. In other words, momentum has been conserved. The initial momentum of the system is the same as the final momentum of the system. And now let's consider the situation from the point of view of a moving reference frame. And by definition, this moving reference frame is going to be riding along with one of the objects prior to the collision, specifically this object here. So consider the situation then from that reference frame's point of view to look, say, something like this. So I'll be that moving reference frame and I'm riding along with this object like so, and the other one comes in, they collide and stick together. Let's consider the situation from that point of view. Okay, so now, according to O prime, where specifically the velocity of O prime, myself, with respect to you guys, the stationary reference frame O, my velocity is equal to v. So I'm riding along with that first object as I indicated. Okay, now right over here, from last time in class, is the Lorentz transformation. What we're going to to do is use the Lorentz transformation to describe the velocities of the objects prior to the collision with respect to O prime and after the collision with respect to O prime. So in other words, we're correctly taking into account now relativistic effects. So let's then picture the collision according to O prime in the following manner. Okay, right here is the first object of mass m, and then with respect to O prime, it has a velocity we're going to refer to here as v1 prime. Now this should be equal to 0 because remember how I'm setting this up. I'm setting this up such that O prime is riding along with the first object there on the top board. So then therefore the velocity of that first object with respect to O prime, it should be equal to 0. So let's see if it is. We're going to calculate it rather by using right here the Lorentz transformation. So now v1 prime, I'll write it out, is going to equal the velocity of number 1 with respect to the stationary reference frame O. That's the V up there on the top board. And then minus U, the velocity of O prime with respect to O, which is V. And then yes, the numerator here is equal to 0, but just to be complete about this, the denominator is going to be 1 minus V times V over C squared. However, as I said, the numerator is equal to 0. So then therefore, once again, this is how we're setting it up. We're setting it up such that O prime is riding along with the first object prior to the collision. Okay, and then we have the second object. Okay, right here is the second object of mass m, and it has a velocity with respect to the moving reference frame. We're going to call this v2 prime. In order to calculate it, we have to use the Lorentz transformation. So then here's how we apply the Lorentz transformation for this object here. This will be now v2 prime, the velocity of this object relative to this observer, and that's then equal to the following. This right here now is the velocity of the second object relative to the stationary observer up on the top board. That's negative v, because remember that the second object is initially moving to the left-hand side, like so. And then minus the velocity of O prime with respect to O, that's still v. And then the denominator of the expression will now have 1 minus negative v times v over c squared. So if you do the math there and simplify some things a little bit, you end up with negative 2v in the numerator, and then the denominator, the negative signs cancel, you end up with 1 plus, rather, v squared over c squared, like so. So now using these values here, let's go ahead and total up the initial momentum of the system with respect to O prime. I'll do this on the right-hand board. We're going to call this P initial prime. So P initial prime now is as follows. We're going to have here, first of all, the initial momentum of number 1 with respect to O prime. That's going to be m times v1 prime. Plus then right here, the initial momentum of the second object with respect to O prime, that's going to be m times v2 prime. And now let's go ahead and plug in what we calculated for v1 prime and v2 prime by using the Lorentz transformation. So v1 prime, remember, is equal to 0. And then v2 prime is this guy here that we calculated. So m times negative 2v over the quantity v, 1 plus rather, v squared over c squared. If you clean this up a little bit and simplify some stuff, you basically just end up with this. So, okay, now let me do a little bit of erasing here on the board. Okay, there's these values that we calculated a few moments ago by using Lorentz transformation before the collision. And now let's see what happens after the collision. So after the collision now, the objects stick together. So there's the 2m, and then let's just draw it like so. We have here now a v final prime. Once again, we're going to use the Lorentz transformation, however, to figure out what this is equal to, because we're taking into account these relativistic effects. All right, so over here, using the Lorentz transformation now, v final prime is as follows. First of all, right here we have v final with respect to the stationary reference frame. That's 0. Okay, minus then our value of u, which remember is equal to v in this description. And then the denominator of the expression we're going to have here, 1 minus v final, which remember is equal to 0. So then therefore the denominator here is just simply equal to 1. simplified, we end up with this value here for V final prime. So now on the right-hand board, let's go ahead and calculate out the final momentum of the system with respect to O prime. We'll call this P final prime. Okay, so P final prime is going to be 2m times V final prime. Like so. Plug in what we just calculated, however, for V final prime, and you end up with this value. So now take a look at the result that we've obtained. This right here is the initial momentum of the system prior to the collision. This right here is the final momentum of the system after the collision. Notice that the two are not equal to each other. P initial prime does not equal P final prime. This is a violation of the first postulate of special relativity. Recall what the first postulate is. It says that the laws of physics are the same in all inertial reference frames. So we have here two inertial reference frames, O and O prime. Up on the top board, according to the stationary observer O, momentum is conserved. In other words, the laws of physics hold. But now here on the bottom board, according to this inertial reference frame O prime, momentum is not conserved. In other words, we appear to have here a violation of the laws of physics. This is specifically a violation of the first postulate of special relativity. Let me write that out for you here. This is a violation of the first postulate special relativity. Once again, the first postulate is that the laws of physics are the same in all inertial reference frames. So something here is wrong. Now, we have correctly taken into account, through the Lorentz transformation, relativistic effects involving velocity. So what we calculate for all these V primes and so forth here on the bottom board, all of that has been done correctly. What is the only other quantity that is present here in this situation, which now also must be relativistic? And that's mass. Mass must be relativistic as well. So because mass is relativistic, this then means that how we describe forces, F equals ma for example, how we describe momentum, how we describe energy, all of that now has to change. So the key to understanding relativistic dynamics is what is called relativistic mass. I'll get to that in part 2 of this lecture.